Okay, so I've got a bunch of problems. If you have suggestions for problems, please do not hesitate. Um, I'd like to do some examples from sections 1.1, 1.3, 1.4, 1.5, and such. Okay. Um, Here's a first example from section 1.1. This is problem number 33. C. Okay, so we're asked to sorry, asked to admit somebody. Here we go. Yes. Okay. So we're asked to do the truth table, to fill in the truth table for the following Boolean expression, which is P or Q XOR P and Q. Okay, so what I'm going to do here, just to show you maybe a slightly quicker way of doing truth tables. This is a simple example when you're doing them by hand. Okay, so faster method. Some people prefer this one, others don't. It's up to you. So first thing, you look at the number of variables you have. We have 2 variables, P and Q. So that's 4 rows in our truth table. So let's just write that up. So true, 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 false, false, true, false, false. These are the 4 possibilities for P and Q. And I've got P or Q, X or P and Q. Okay, so I could, the previous way I've shown you, although very briefly, how to do it is to build it up with more and more columns, but you can actually do it in the following way, where you you write down below the smaller expressions that you're evaluating their values, and then you fill up from, or fill in, fill up, fill out from that point. I'm not going to, obviously in this case I could just copy down the values for P and Q below these variables, and I'm not going to do that. I'll just start by evaluating the or and here. Sorry, made some tea, we'll drink. Okay, so the or, again, quick reminder, or is true as long as one of them is true. So this will be true, 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 and this will be false, right? So below P or Q, I'm just evaluating that expression. The and is true when both are true. So this will be true, false, false, false. Okay, so I've evaluated the 2 brackets, and now I can evaluate the XOR, which is true when exactly one of them is true. So this will be false, this will be true, this will be true, and this will be false. So this is the resulting values for the whole expression. Notice, by the way, that this actually shows that this complicated expression is actually logically equivalent just to XOR. Okay, so just a little, if I just write the XOR here, you see that this is false, true, true, false. So it turns out that they are actually logically equivalent. So the or and in this expression just don't do anything. Okay. But I wanted to illustrate how I built the table rather than building more and more columns, which you can do if you want, but it's a bit shorter to do it this way. Um, so hopefully this makes sense. Here is now an example from 1.3. Let's do that one. I mean, if there, of course, if there are questions, jump in, chat, raise your hand, whatever. Open your mic. All is good.
Can we do like eventually in the session like a problem on like converting like a decimal to binary and then to hexa?
Ah, man, my camera is still freezing. I don't know why this does this. This does that.
For us, it's good. We
It's good, yeah. It's me. I don't know. It's my own Zoom. Maybe I have to update it. It's the first time in like more than a year that I've had this problem. Um, yeah, somebody asked me this. Yeah, I should yeah, about crap. About the WebWorks. Uh, I said do them by hand, and anyway, you got them all right, right? So, but because you took a calculator, and that's fine. I had a brain cramp converting decimal to binary. Sorry, from binary to decimal is easy, right? So if you go from binary to decimal, you should be able to do that. Basically, you just read it off, right? So you just, that's easy, right? You just read it.
what do you mean by read it?
I'm going to show you. So
Oh,
for
okay.
example, if I have 10011 0 in binary, right? I want to convert it to decimal. Well, I need to know what, I mean, what does that mean? So these are powers of 2, right?
Yeah. Okay.
0,
Yeah.
1, 2, 3, 4, 5. So this is 1 times 2 power 5 plus 4, 3, 2. 1 times 2 power 2. 1 times 2 power 1. Right? I'm just interpreting the notation. So this is 32 plus 4 plus 2, which is 38. Right? So that's what I mean by converting from binary to decimal. You just basically expand the notation, what it's supposed to mean, right? Is that okay?
Yeah.
All right. So the other direction I didn't talk about, if you want to go from, why am I writing this always backwards? I don't know. If I want to go from decimal to binary, so I didn't talk about that. And again, sorry, brain cramp on my part when I put those into the WebWorks. I actually didn't see them, didn't notice them, didn't think, I don't know. If you want to go from decimal to binary, it's a bit trickier. You have to do successive divisions by 2. I didn't talk about that, and I'm not sure I want to talk about that. So for now, so sorry that you saw those in the WebWorks, but of course you could do it with Google calculator, whatever. But for now, let's skip that. Okay, let's not worry about that. Okay, so forget
Okay.
this.
So it's not gonna be on the test.
Nope.
Okay. Because like I found the method in the internet, but
Yeah, yeah. So sorry, this is my mistake. So forget this for now. I mean, we have tons of other stuff to do, so it's just this is okay. So it's successive divisions by 2.
yeah, no worries.
Successive divisions by, so if you're curious, that's what you do, but you don't need to know that. Okay, so let's just don't worry about that. Okay, number 29 in section 1.3, we're asked to show that if P then Q and if Q then R, if all that, then if P then R. So here's a good place where rather than say if then, just use implies. So P implies Q and Q implies R implies P implies R. So if you pay attention to this thing, show that, yeah, that's show that is a tautology. There's something missing. Tautology. Okay, so if you just look at what this says, it's the transitivity of implication. Okay, so notice This is transitivity of implication. What I mean by that is if you know that P implies Q and you know that Q implies R, then you can deduce that P implies R. Okay, so if you start with P, then you can conclude R safely because you know that from P you can conclude Q and from Q you can conclude R. So that's the big picture, okay? But how do I show that such a thing is a tautology if I want to do a absolute total foolproof proof? Then I will use a truth table, okay? So okay, so let's take a look at this. So I've got 3 variables, right? We have 3 variables involved, P, Q, R. So that means 2 power 3, 8 rows for my truth table, right? So let's copy this like that. Let's move to the, you know what? Let's just go here. Let's paste this here. Why does it say lol? I don't know. Okay, so let's do our truth table. 3 variables PQR like this. P implies Q and Q implies R implies P. Is that here? Yes.
Yeah, we do.
Yeah, but sometimes I don't know if I'm picking because yeah, yes. If I'm hearing one of your microphones, which is still open, or is coming through mine, I have the headphones, so it's difficult to know where it's coming from. So okay, true, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, and false, false, false. All right. So what I'm going to do is I'm going to proceed just the way I did. I realize that's a big one, but anyway. So I'm going to evaluate these things here, here, and then here, and I'm going to finish off with, so this is also a good exercise to see how you're parsing this whole thing, right? So clearly the last thing you're going to evaluate is this implication. That's the very last thing you're going to evaluate, right? So you need the value on both sides, okay? To get the value on both sides, so this one, okay, I'll start with this one, that'll be easy. To get the left-hand side, I'll need to evaluate both of these first and then take the ands, okay? So we have to do this in obviously in the proper order. Okay, so let's start with the very last implication. I'm looking at the values for P and R. So we know this implication is true unless P is true and R is false. So that's the bad guy. So this is true, false, then true, then false. And the other one should all be true. Okay. I guess once you get used to it, the hardest thing to do here is to get things to line up. So, okay, let's do P implies Q. P implies Q, same thing. This is always true unless you get true, false. So this is false, false, true, 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 true. Okay, then Q implies R, same thing. So this will be true, false, true, 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 false, true, true. Okay, so I'm just evaluating the 3 implications. Next, I need to evaluate this and. That's easy. So that's true, false, 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 true, false, true, true. Okay, so now this is the value of the left-hand side. This is the value of the right-hand side, and I'm going to evaluate my implication here. So again, implication will be true as long as I don't have true, false. So this will be true, 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 and true. And I've got a tautology. This is always true. Yeah. By the way, I don't know how silly this is going to sound. If all of you find this silly, that's fantastic. Suppose that you're asked to prove something is a tautology, and you don't get a whole bunch of truths here. You have two possibilities at that point. You can either say, this is not a tautology, or you can say, I made a mistake, I'm going to recompute. The second option is the right one, okay? So if you're asked to prove something's a tautology, it is a tautology, unless whoever's asking question made a huge mistake, okay? So, but that's the unlikeliest possibility, okay? So if you get a column which is not all true, then something went wrong, just do it again, okay? So yes, okay. So that was a more involved example of how I build the table, but you see it's not too bad, it's not too long. That was actually one of the bigger examples you can get on 3 variables. So, I mean, of reasonable size, a big one of reasonable size. Okay, number. Okay, so I think this one is not in the list, but no, not number 1.3, section 1.3, number 29. I'm not sure if this is in the 27. I just did 29. Number 27, we're asked to show, I'm not going to do this one, but I'm just going to write it up because it's something I didn't talk. I don't think I may, it's in the slides somewhere, but I didn't spend too much time on it, if at all. So we're asked to show that if P then Q and if Q then P is logically equivalent to P if and only if Q. Okay, so I'm not going to solve it, but I just want you to pay attention to this. You see the notation, you remember if and only if is true when both have the same truth value. Okay, so that's the way we define this guy. We just said it's true when both have the same truth value. But you see the notation is interesting because this is where it comes from, right? So if you have P implies Q and Q implies P, right? It's like arrows in both directions. That's where the notation comes from. Okay, so notation comes from this. Okay, so it means that if P then Q and its converse both are true, that's the same thing. Okay. All right, so I'm not gonna do the table for this, that you can do that. I'm not sure it was in the list of problems, but as long as you see this, okay, let's
I
again.
have a question.
Yep, please.
What's the inverse of a statement if I have a preposition?
Yeah,
Like, usually-
I forget about that. Never used that. Not even sure. I have to look it up. Nobody uses that. I don't know why it's in there. I removed it from the exercise. Man, it's so annoying, this freezing camera. It's really annoying. But anyway, I have to stop just looking at myself. Bad habit. Okay, one point.
Sorry. Also
Yep.
for number 27, since basically the statement on the left is basically the definition of what's on the right, could we simply say that instead of doing a truth table?
Well, as I said, that's not really how we defined. I mean, you can define it that way, but that's not really how we defined it, right? We defined P if and only if Q by the truth table, saying it's true when, so So this actually was defined as follows. P if and only if Q. I mean, for me as a mathematician, yes. I mean, what's written there, that's for me, that's the definition of P if and only if Q. But the way we defined it here was with the truth table as follows. So we said true, true, this is true, true, false, this is false, false, true, this is false, and false, false, this is true. Okay, so the statement here says that the truth table of this thing on the left is that. Do you see what I mean?
Yes, thank you.
Okay, but I mean it's not a big deal, right? It's not as I mean it's important to know that these are the same thing, right? That's basically what's at stake here. Okay, I spotted an interesting one. Here it is. This is in section 1.4. It's number 23. I have to go to the book because the question is a bit. It's. I mean, some of these questions are a bit strangely formulated, but let's go here. Where is it? Where are you? Yeah, translate in two ways each of these statements into logical expressions using predicates, quantifiers, and logical connectives. First, let the domain consist of the students in your class, and second, let it consist of all people. I wouldn't quite phrase it that way. I'm going to phrase it this way. So convert to FO the following statements. The first part will be the domain is students in your class. And in a second exercise, the domain is all people. Okay, so I'm just going to write down the statements here, and then I'll provide some extra information. So I won't do all of them. You can try later on. You can try the later ones. That's a lot of lights. Someone in your class can speak Hindi. Someone in your class can speak Hindi. Second, everyone in your class is friendly. I hope that's true. C, there is a person in your class who was not born in California. So there is a person in your class not born in California. Okay, so I want to convert these as first order statements. First, when the domain is the students in the class, in our class, let's say, okay? And then we'll do it when the domain is all people. So first of all, I need symbols for the predicates involved, okay? So let's take a look at what I'll need. So so again, now I'm in part one. The domain is students in your class. So for A, I'll need the predicate can speak Hindi, right? So I'll call that H of X. X can speak Hindi. Okay. For B, I'll have being friendly. I'll call that F of X. X is friendly. And for C, to be born in California. So let's call that big C. So X is born in California. Okay, so I'm just going to move that up a little bit. So A, someone in your class can speak Hindi. The domain is the class. So there exists an X, H of X. That's it, right? That's all we need. B, everyone in your class is friendly. You can guess. So everybody satisfies f of x. For every x, f of x. Everybody in the class is friendly. Okay. And C, X is born in California. There is a person in your class not born in California. You can guess. There exists an X such that not C of X. Okay. So that's my empty stomach. Sorry about that. Okay. So second part is the domain is all people. So now you look at those statements, and I have to add something because I have to specify the quantification is not over all people, but over people in the class. So I'm going to add a predicate for being in the class. Okay. So for 2, so domain is all people. Okay, I will use a new predicate, which will be, oh man, let's call it D for discrete math. D of X. X is in the class. Okay, so I'm gonna use this predicate to specify that somebody is in the class. Okay, so now what I want to do, let's copy this whole thing. Copy. Let's go here. Let's paste this like that. Ooh, this is nifty. Let's erase. No. Let's erase those. Okay. Let's do that. Let's put that here. Okay. All right. So now statement A, someone in your class can speak Hindi, but now the domain is everybody. So I'm going to use this new predicate. So there exists an X, but now I have to say that this person is in the class. So the person is in the class and can speak Hindi. Does that make sense?
Yep.
Yeah, good. Excellent. B, everyone in your class is friendly. So now I have to say for every X which is in the class, this person is friendly. Actually, this is such a good example. I mean, that's a really good one to think about. So for every X, but now I have to quantify over, I'm only for people in the class. So it says that if somebody is in the class, anybody, then they are friendly, right? So for every X, if X is in the class, then X is friendly. So everybody in the class is friendly. So that's how you write this if you have a restricted domain for your quantification. That's exactly how you do it, okay? Last one, there is a person in your class. This is actually the same as A. So there exists a person which is in your class and not born in California. So D of X and not born in California, like that. Okay, so you see it's a bit trickier when the quantification is not over the whole domain, okay? But then this is how you do it, okay? Okay, hopefully this I mean, this is a really very, it has a lot of good information, this problem here. I like it. Okay. Any questions?
For B, it's an arrow because like it's dependent of the fact that the person needs to be in the class in order to be friendly.
Yeah. I mean, how else are we going to do this? So, but what you want to say is everybody in the class is friendly. So you obviously, if you're going to say everybody, you're going to have to use a universal quantifier. So for sure, we're going to use that for all X. But now for all X, that quantifies for all people, which is not what I want. I want to say everybody that is in the class is friendly. So for every X, now I have to say what? I have to say if the person is in the, I don't know, I'm just repeating what's written. I'm sorry.
Yeah, but no, I understand. I understand.
Yeah. I mean, you're not going to be able to express this with or, and, or negation. I mean, yeah, you can, because you can re-express the implication. But it's not going to help if you write it as, yeah, you could say either the person is not in the class or this person is friendly, but that's exactly the same as what's written here. It's logically equivalent to that. But I'm
Okay.
not sure. Would you think of it as an if that? Yes, if you're talking about this, yes, that's exactly. So if this person is in the class, anybody in the class, then this person is friendly. That's, yeah. So the only, I mean, that means everybody in the class is friendly. For every X, if the person's in the class, this person is friendly. I'm sorry, I'm just I'm just repeating
No,
the
I
same thing
understand. Thank
over and over again. I don't know how to explain it, any other way. That's the way it is. Learn it. Nah. Okay, let's move on to number 31. 31. I have to say a few things about this, which some of them are annoying, some of them are pretty cool. Number 31. So 31 is okay. So by the way, strange formulation. I'd have to go back. I'd have to go back to the book, but when I defined predicates, I gave the domain of a predicate as, so let's say the predicate has 3 variables. I said the domain is x cubed. So in other words, you can plug in any triple of values from the domain in that predicate. Here, they're giving you a restricted domain. You see that some triples are not allowed in a sense. Okay, so here's a remark. I mean, this is totally legit, but I wasn't expecting this looking at the problem. So here, they restrict the domain of a predicate to, and I'll just write it as a product. It's easier. It's 0, 1, 2 times 0, 1 times 0, 1. So they're saying that X can be 0, 1, or 2, Y can be 0, 1, and Z can be 0, 1. Okay, it's for the 3 variables X, Y, and Z. So the predicate is called Q of X, Y, Z. Now, how I define predicate, X, Y, Z should be able to take on all possible values in some domain. Here they make a restriction. That's okay. I why not? Okay, so here's an example of where you might have to do this. So example where this could be needed. So in other words, I wasn't general enough when I gave my definition, but it gets just technical and annoying. So here's an example. Let's say I define Q of X, Y, Z to be Z equals, let's not call it Q because you'll confuse with this one. Let's call it S. No, not S because we keep using S for, let's call it, B. Okay, B of X, Y, Z. Z is equal to X divided by Y, and the domain would be, let's say R. Okay, so you see that in this case, you can't plug in all possible values, real numbers for X, Y, Z. You have to prevent Y from being 0. So here must restrict domain of B so that Y is not equal to 0. Right? So if you're going to construct predicates like this, then you have to make restrictions, and so you have to restrict the domain. I don't want to go there. But in this particular example, they did that, although it's not really necessary. That's not the point of the exercise, okay? But I'm not going to use that, okay? So you shouldn't worry about that. So let's go to that example that they're giving us. So we have Q of X, Y, Z, and the domain of Q is 0, 1, 2 times 0, 1 times 0, 1. So the triples, the only triples that Q can light up as true or false come from this set. Okay, so X has to be in 0, 1, 2, Y has to be in 0, 1, and Z has to be in 0, 1. And now they ask us to write out, so write out the following propositions using or, and. Okay, so the first one they give us is for all Y, Q 0, Y 0. Okay, now this is interesting. So in my experience, students look at this and they go, I have no idea what's going on. And then when I explain how it goes, they go like, oh yeah, that was easy. So the fact here is that the domain is finite. Okay, so a for all statement, you can actually just expand it. So how would I illustrate that? So look at the commutative law for the sum for integers, right? It says, what it says is that for every x and y, x plus y is equal to y plus x, right? But I could make a list of all possibilities, which is 1 plus 2 is equal to 2 plus 1, 1 plus 3 is equal to 3 plus 1. And you can list them all, except it's going to be infinite, right? So it's not a legit formula. But if you have a finite domain, you can just expand the whole thing. It's going to be finite, and that's exactly what you mean to say. So what does this say? For every y, q of 0, y 0, remember what it means. It means that q of 0, y 0 is true for every possible value of y. So this is the same as saying, and I'm just going to replace every possibility for y. So q of 0, 0, 0 is true, and q of 0, 1, 0 is true. That's it. That they mean exactly the same thing. So the for all is a way of transforming infinite stuff into finite stuff, right? So because you can always just list, you can always just, that's what it means, the for all, just this is true and this is true and this is true and this is true, the whole bunch. But when you're doing logic, I mean, some people do logic with infinite formulas, that's something else. Okay, but in what we want to do, if we want a machine to actually handle these things, then we need something that's finite. So the quantifier is there to compact the whole thing. Okay, so if the domain is finite, then that's it. Okay, so let's try. Hopefully this is clear. I'm not rambling, or this makes sense.
Why do we not use like the 2?
Because y is restricted to 0, 1.
Okay.
Yeah, x can be 2, but y is not allowed to be. But you can
Okay,
do
okay,
this.
does it mean that x can be 0, 1, 2,
Yes.
y can only be 0, 1, and z can only be 0, 1? Okay,
In that,
okay.
yes,
alright.
yes, that's it. Exactly. B, there exists an x such that q of x 1, 1. Okay, so again, what does the existential quantifier mean? There exists an x such that q of x 1, 1 means that q of x 1, 1 is true for at least one value of x. But what are the possible values of x? There are 0, 1, 2. So this is exactly the same as saying that either this is true for x equals to 0, or it is true for x equals to 1, or it is true for x equals to 2. Right? So these are the possible values. So these are all the possibilities for x. Okay, so again, the existential quantifier is a way of transforming infinite formulas into a finite thing, right? So because it's an or, either that one is true or this, and you do the or over all the possible values for your variable, but that's infinite. So if you want it finite, you have to introduce, that's the idea of the existential quantifier, one way of seeing it. Like this. So universal quantifier, existential quantifier. So these refer to possibly infinite things. If your domain is infinite, if the domain is finite, it changes nothing. As you can see, you can write that you can write everything without the for all or there exists. It's possible. Okay. I won't do the other two because they're basically the same. They're C and D are just very, very similar. But keep that in mind when you have a finite domain. You can rewrite existentially or universally quantified things as just long sequences of ands or ors. All right, that's done. This is good. This is an important one. Let's go to 1.5. Oops. Example 14, actually. So I talked about this in the slides, but I went over a bit quickly. So I'd like to do this a bit more slower. So here is a statement. The statement is, for every x, there exists a y such that xy equals to 1. So presumably the domain is R. This is the product of real numbers. That's the 1 for real numbers. It could be integers, but anyway, so you need somewhere where this product and this 1 means something. So this is a statement, could be true or false. It's not relevant for us right now. So what I want to do is to do this. So write the negation of this statement where quantifiers precede any don't do that, negation symbol. Oh yeah, by the way, so the twiddle in this Really? This tilde that you may have seen in the WebWorks, it means negation. Okay, the tilde that you've seen in if you've looked at the WebWorks, there's a couple of tables where they give you expressions with this tilde. It means negation. Sorry, I should have mentioned that. Okay, let's. All right. Okay, so I want to negate for every x there exists a y such that xy equals to 1. What I want to do, I'm going to do it mechanically, but we'll try to keep track of the meaning of the whole thing, and I think this is important. Okay, so negation of for all x there exists a y such that xy equals to 1. So I want to have my quantifiers in the front. Okay, so what do I need to use? If you think back to last class, I talked about De Morgan's laws for quantifiers. When you're negating a for all, it becomes an existential quantification, right? So it is not true for all means there exists some bad guy, right? So how does this work? The negation goes inside and the quantifier is flipped. So let's just do the first step mechanically. So I'm going to take the first quantifier, bring it out. It becomes an existential quantifier. Negation goes in. The rest stays the same. Okay. So not for all x blah, blah, blah means there exists an x such that not blah, blah, blah. Right. So think of it logically. Hopefully it makes sense. So what's after the for all x, that's the property that's satisfied or not by x. So if it's not true for all x, then it's false for at least one x. That's what this
I have a
says.
question.
Yes.
Why would the negation of for all not be for none? Why is it for or there exist?
Okay, so if I tell you, so I mean, every tree is a maple tree, right? Why is that not true? It's not that no tree is a maple tree. It means there's at least one tree which is not a maple tree, because my statement, my claim is that every possible tree is a maple tree.
Okay.
Right? So that not being true means, well, there's at least one tree which is not a maple tree, rather than there are no maple trees.
Okay.
Right?
Perfect.
You see
Yeah.
what I mean?
Yeah. So the there exists would be sort of a minimal condition, and the for none would be exceeding that. Anyways, no, I get it with your example. It's fine.
Yeah. Yeah. So yeah, if I'm saying, or let's do the other one. Maybe that's, I mean, they're equivalent, but suppose I say there is at least one person in the world that is 3 meters tall. What is that? I mean, this is, if it's false, it means nobody is 3 meters. But so it's not that everybody's 3 meters tall, or, I mean, okay, let's erase completely the last 30 seconds, which were just confusing. Let's just not think about what I just said. Okay, so everybody is 3 meters tall. That is not true, because I can find at least one person not 3 meters tall, right?
Okay.
But it's not it's not relevant to the fact that nobody's 3 meters tall. That's something different.
Yeah. Okay.
Right? Okay.
Thank you.
Okay, so I've reached this point where I've got there exists an X such that not blah, blah, blah. So now I still have a quantifier inside that I need to bring out. So I'm going to use de Morgan's law once again. So again, existential, if you negate, means for all. So again, think about it. This statement here says there exists something, and I'm negating that means there does not exist. So it means that for all, not the property, right? So let's not used to this thing. Okay, so there exists an X that stays there. So now the exist Y will become for all Y, negation of XY equals to 1. Okay. So the so my original statement was for every X, there is a Y such that XY equals to 1. In other words, for every, let's say, real number, it has an inverse. The negation of this is there is at least one real number that does not have an inverse. Okay. And how does that, is that written is exactly the way it is here. There exists an X such that whatever Y you choose, Y is not the inverse of X. XY will never be equal to 1. You could also rewrite it as this because we have a special symbol for that. That's maybe a little easier to write, but formally this is the previous one, which is the right one. That's fine. Okay. So you can do it mechanically, but to make sure you're not messing up, you can interpret at each step what's going on, right? Hopefully this made sense. Just please try to thinking about that little 15 seconds of just whatever happened there. I don't know. Okay, does that make some sort of sense? Yes, hopefully.
Yeah.
All right. I'm almost done. 41, that's not 41. Oh yeah, because I'm not in the right. 1.41. Yeah, I'm going to do, I mean, this was actually in the list, but this is still from 1.5. I really don't know why this problem has such a high number, because it's really, I mean, so the question is this. So use quantifiers to express the associative law. For multiplication of real numbers. So this is, I'm doing this because I talked about this very briefly in last class. I said, in the last few years, you saw a lot of identities, right? But they were not expressed quite correctly in the sense that we skip some stuff because otherwise it's painful. But it's the universal quantification was always skipped, which to some extent eventually creates confusion. So here's the question. I want to use quantifiers to express the associative law for multiplication. What is the associative law for multiplication? It says that if you take any three real numbers, you can multiply them with any bracketing you want, and you're going to get the same answer. That's the associative law. So we usually write this as follows. X times YZ equals to XY times Z. This is something we tend to forget about because it's so basic. But if you do a little more advanced math, you'll eventually run into things that don't satisfy the associative law, and then you'll miss it dearly. It's like a wonderful, wonderful property to have. If you don't have it, things get really, really messy. Oh, okay. But so this is the way you would usually see them, but that's not the associative law. This is not even a proposition, right? So the right way to write this is for every x, for every y, for every z. This is the correct associative law for multiplication if the domain is, let's say, real numbers. Okay, so this is true for all possible choices of x, y, z. This is not the hardest exercise in the book, by the way. I mean, that's the answer. They're really very straightforward. But I wanted to talk about it because, so in a sense, all the identities we tend to not write the universal quantification or not saying, but it's fundamental. It's really fundamental in the statement. Anyway, I'm rambling. So that's pretty much the problems I wanted to do. I'm not doing, if you looked at the list of problems, I haven't assigned anything from 1.6, rules of inference. I mean, if I had an infinite amount of time, I might do a few things in there, but I don't. So actually, I can save you lots of time. There's a table on page 72, rules of inference. Actually, just you only need one, and I'll talk about that next week. And I'm going to start proofs. And don't be scared. This is great. Don't be scared. Okay, so that's all I can say. Any questions, comments?
For the exam, is it the chapter 1 and 2 of the book, or is it we're
Yes.
gonna go?
Yeah. Nope, that's it. Once I finish chapter 1, that'll be the material for test 1.
And do you recommend us reading the book or just looking at or just watching the lectures?
Yes, I do recommend reading the book, obviously. Yes, I do. Yeah, I mean, it's always good. It's for sure. The only thing I would say is the only thing is, if you see something in the book that I didn't talk about and it's not in the exercises, then you should safely not, if you're thinking in terms of the test, you skip it. That's the only thing. So I pick and choose. So that's the only difficulty I would say here is that, is that I'm skipping some stuff here and there. I don't think I've modified too much notation or definitions. If I didn't say so, I just really followed the book. So that's safe. So if you're reading the book, it should match exactly what I'm doing. But that's the only caveat. Obviously, you can probably manage without reading the book. I shouldn't say that, but I mean, especially in these very weird times. But yeah, but of course, if you have time, if you can just go, yes, it's a good read. It's a good book. Sorry, long answer.
Okay, thank you.
Anything else? Okay. All right, so that'll be it for today. I will stop recording.